Today we're going to be talking about graphing absolute value functions, and we've already talked about translations of functions. So this is the standard form of an absolute value function. The vertex, or the lowest point, is going to be hk. So notice if it's x plus h, it's going to go to the left if h is negative. If it's x plus h, and it's to the right if it's x minus h. And then plus k, you go up, minus k, you go down. Since an absolute value function looks like a V, where these are straight lines, what the A is the vertical stretch or compression. Because these are lines, A is essentially the slopes of these sides. If A is positive, we open up. If A is negative, we open down. So now graphing this function, plot your vertex. Our vertex is 4, 3, because minus, remember, you go to the right. So we plot our vertex, 4, 3. The 2 tells us the two slopes of our sides. So we go up 1 over 2, up 2 over 1, up 2 over 1, up 2 over 1, and the same thing on the other side. Just these are the negative versions, and then we have our absolute value graph. Now here, our vertex, put it in standard form, so you have to make this x minus a negative 5. So our vertex is negative 5, positive 7. So negative 5, positive 7. And then I go, now since the A is negative, we open down and I go down 1, right 3, down 1, right 3, and down 1 and left 3. And notice how you have some symmetry points going on there. So that is what your absolute value graph looks like. Now this one's a little bit more complicated. Whenever you have something that's being multiplied to the x, what you need to remember to do is when it's inside the absolute value function or inside any function, your transformations are a little bit backwards to what seems obvious to people. If you have to factor out the 1/2, when I factor out that 1/2, what times 1/2 is 4? That's going to be 8. Now, technically, this is a horizontal stretch because it's inside the function and it's opposite of what it seems. But because of how absolute value functions work, that's really the same thing as these slopes like we've been doing. So I go, my vertex is negative 8, 0, so I go to negative 8, 0. And it's a horizontal stretch, so instead of going up 1 over 1, this 1 point that would be up 1 over 1 from our normal gets stretched over to 2. So really it's the slope of up 1 over 2. And so that's what our graph looks like. The key thing, again, remember, factoring out that 1/2. Okay, now writing the equation. You need to figure out your h and your k. So our h is 2, our k is 3. Now you need to figure out the a, or the slopes of both sides. We know a is negative because it opens down. Now count out from one point to another your slope. Down 1, 2, 3, 4 over 1. So now it's just a matter of plugging in. Y equals a x plus 2. I apologize. I should have gone with my instincts. That's actually a minus 2. Plus 3. What I did there is I did a quick check. Minus 2 means left 2, or right 2, I apologize, right 2, which that makes sense. And the 4 is negative because we're opening down. If you go from your vertex always to the right and count out your slope, that's inherently, because I went down 4, right 1, that gets you the negative version that you needed. Our next example. Again, let's figure out our h and our k. H is 1, 2, 3, 4, 5, negative 5. And k is negative 4. So now we have y equals a x minus h plus k. So that's going to help you guys. If you write out that standard form first, that's going to help you guys get the right thing. A is positive. Looks like we go from that point there up to that point there. We go up 2, right 3, up 2, right 3. So now it's just a matter of plugging in. 2/3 x minus a negative 5 plus k. Oh, plug in your k, Marnell. I'm trying to rush through this. All right, so we have a minus a 4. So that's our equation there. Okay, there are your lesson questions. So please make sure the summary and your lesson questions are submitted on time.